you carve out the stone to remove stone so that you have these giant pillars with like a lizard crawling up the side of it, but the lizard extends out from the stone.
Yeah, high relief.
For as long as anyone can remember, the pyramids have inspired awe and questions. How did the ancient Egyptians carve and move enormous stone blocks with such precision without cranes or power tools?
I don't think anybody knows how they did it, how they lifted those stones, how they brought them up to that level. I think we're looking, again, at a lost technology. And it was this ancient apocalypse 12,800 years ago that wiped that from the human memory banks almost completely.
Generations of researchers have debated the how and even the how could humans do this. Now, after decades of experiments, digs, and careful study, we finally have answers. And the truth is more incredible than anyone imagined. The cutting finally cracked. The precision of ancient Egyptian monuments has defied explanation for a long time. The pyramids, obelisks, and massive temple blocks sit so perfectly aligned that even modern engineers marvel. Each stone, some weighing tens of tons, was cut, smoothed, and fitted with remarkable accuracy. How did they do it without steel tools, modern machinery, or power cranes? The question has fascinated scholars, engineers, and lay people alike, spawning theories that ranged from the plausible to the fantastical. Early theories were imaginative, but often misguided. Some suggested alien technology or lost mystical knowledge. Others believed the Egyptians must have had tools far superior to anything archaeologists had found. Tools that would make our modern equipment seem primitive. These ideas, though sensational, persisted in popular imagination because the evidence seemed to defy human capability. After all, how could copper chisels carve granite with such precision? How could thousands of massive blocks be moved into place with nothing but human muscle and ingenuity? The first real breakthrough came from examining the quarries themselves. Sites like Aswan, the source of granite for temples and obelisks, and Tura, where fine limestone was extracted, revealed tool marks that told a story long ignored. On unfinished blocks, researchers found grooves, scratches, and wedge marks consistent with repeated abrasion, not sheer force. Copper chisels, combined with sand as an abrasive agent, could carve softer limestone relatively easily, but granite required something more. Here, sand became the real hero. Quartz grains, dragged across the stone by copper tools or wooden guides, gradually cut through rock, leaving surprisingly precise surfaces. Experiments over the last few decades have reinforced this. Archaeologists and engineers recreated ancient cutting techniques using replicas of Egyptian tools. With copper saws, wooden guides, water, and quartz sand, they managed to shape stones almost exactly like the originals, though at a slower pace than the ancients likely achieved. These experiments proved that, contrary to some theories, no unknown technology or lost super tools were necessary. Human ingenuity, patience, and clever use of available resources were enough. Even more intriguing was evidence from the so-called unfinished obelisks at Aswan. These massive stones, still attached to bedrock, bear marks of chisels and wedges, showing the sequence of work the Egyptians followed. By analyzing these marks, researchers realized that the ancient builders had developed an early form of project planning: careful measurement, step-by-step extraction, and continuous quality checks. Blocks were first roughly cut and shaped in the quarry, then polished and finished on-site or at their final destination. This stepwise approach minimized errors and wasted effort, a method strikingly similar to modern project management principles. Despite these breakthroughs, some details remain under investigation. The precise speed at which workers could cut and shape enormous blocks, the exact number of laborers involved in massive projects like the Great Pyramid, and the complete range of tools used are still topics of research. Advanced techniques, such as copper tubular drills with abrasives for intricate details or small channels, are being studied through experiments and 3D modeling. What's clear is that the Egyptians weren't improvising blindly. They had a methodical system that combined physics, geometry, and careful labor organization. Perhaps the most remarkable aspect is that these techniques are simultaneously simple and brilliant. Copper, sand, wood, and water. The materials were ordinary, but the application was extraordinary. The Egyptians understood leverage, force distribution, and material behavior in ways that we are still piecing together. Their ability to translate this knowledge into monumental architecture is a testament to human creativity, not mystery. This discovery changes how we view Egyptian engineering. It shows that the ancients didn't rely on magic or otherworldly intervention. Instead, they relied on observation, experimentation, and collaboration, values familiar to modern engineers, scientists, and craftsmen. Every groove, every polished surface, and every perfectly fitted joint tells a story of centuries of accumulated knowledge and careful practice. The stone-cutting mystery is not entirely solved. There are still unanswered questions and ongoing experiments. But, for the first time, we can confidently say that the Egyptians' techniques were within the realm of human possibility. The sheer scale, precision, and elegance of their work remain awe-inspiring, but it's now a story of ingenuity, resourcefulness, and patience rather than inexplicable power. By combining archaeological evidence, experimental archaeology, and careful analysis, researchers have illuminated one of the greatest engineering feats of history. The pyramids and temples are no longer seen as impossible marvels. They are the products of human brilliance, tested by time and nature. What was once a mystery that surprised almost everyone is now a testament to what humans can achieve when imagination meets careful planning and unrelenting effort. So, what exactly were these Egyptians using to carve and move stones with such crazy precision? Tools, techniques, and materials. For a long time, people imagined that they must have had some kind of super tool or secret method lost to history. The truth is far more fascinating and entirely human. It all comes down to clever use of materials, patience, and surprisingly simple tools that, when combined with smart techniques, could do almost magical things. Let's start with the basics: copper chisels and saws. On their own, these tools are soft and couldn't possibly cut through the hardest stones like granite. But the Egyptians weren't naive. They paired these tools with abrasive sand, often quartz, which did the heavy grinding work. Copper guided the sand did the cutting. Slowly, layer by layer, grooves could be carved, blocks shaped, and surfaces smoothed. Water was added in some cases to reduce friction and keep the dust down, basically turning a simple chisel into a surprisingly effective cutting system. Limestone, being softer, was easier to work with. Craftsmen could shape it using chisels, hammering gently to remove pieces in a controlled way. Granite and harder stones, however, required a combination of techniques. Archaeologists have found evidence of copper tubular drills used to make holes or channels in rock. When paired with sand as an abrasive, even granite could be drilled and shaped with impressive accuracy. Experiments using replicas of these tools have shown that blocks could be carved precisely, and the results match what we see on pyramids, temples, and obelisks. Then there were the wedge and lever methods. After shaping the stone roughly, workers inserted wooden wedges into cracks or carved channels. They soaked the wedges in water, causing the wood to expand and slowly split the stone along the line of the groove. This method allowed for controlled separation of massive blocks from the quarry, reducing the risk of accidental cracks or breaks. In other cases, hammering with stone or dolerite pounders helped refine the shape or smooth surfaces. But cutting the stone was only half the battle. Moving it from quarry to construction site required ingenuity. Sleds and rollers were standard, but experiments suggest the Egyptians also lubricated paths with water or oil to reduce friction, a simple trick that made hauling tons of stone surprisingly manageable. Ramps, both straight and zigzagging, helped workers move blocks up steep inclines. Large teams could coordinate lifting, sliding, and maneuvering stones using ropes and levers, essentially turning human muscle into a precise, collective machine. Even small details show the Egyptians' understanding of physics. For example, tool marks on unfinished obelisks reveal carefully planned sequences of cuts, showing that each step was intentional. There was no guessing, no trial and error chaos. Everything was measured, timed, and executed in a way that minimized waste and mistakes. It's a level of precision that makes modern engineers pause and admire. What's most impressive is how ordinary materials were transformed into extraordinary results. Copper, wood, stone, sand, water, all were abundant and accessible. The brilliance wasn't in high-tech gadgets. It was in how they combined resources, observation, and skill. Simple tools, guided by human ingenuity, created some of the most enduring monuments in history. When you look at a pyramid or temple wall, you're not just seeing stone. You're seeing the story of people who figured out physics, material science, and logistics thousands of years ago, without electricity, without machines, without modern math. So we know what tools they used, but how did they get thousands of workers to cut, move, and place these massive stones so perfectly? Hands that made them possible. Having chisels, sand, and sleds is one thing. Getting thousands of people to work together on massive stone projects is a whole different challenge. The pyramids, temples, and obelisks didn't build themselves, and the precision we see today is just as much about organization as it is about clever tools. Evidence suggests that the ancient Egyptians had a highly structured system for managing labor. Archaeologists have found worker villages near the Giza Plateau, complete with bakeries, dormitories, and even medical facilities. This wasn't a random mob of laborers. It was a coordinated workforce with assigned roles. Some were carvers, others haulers, and still others were supervisors, ensuring the right sequence of steps was followed. Each person had a purpose, and the hierarchy helped projects run smoothly over decades. Specialized teams were a key part of this system. Stonecutters focused on shaping blocks, while haulers concentrated on transporting them. Engineers or master planners calculated angles and measurements, making sure every piece fit perfectly. Even minor errors could have caused massive setbacks, so attention to detail was critical at every level. The Egyptians seemed to understand that large-scale projects only succeed when every worker knows their role and how it contributes to the bigger picture. Timing also mattered. Construction was often seasonal. Some historians believe major projects were scheduled around the Nile's flood cycles, which freed farmers to work as laborers during the inundation months. This gave the state access to a large available workforce without interfering with food production. It was a clever way to maximize manpower without overtaxing society. Coordination went beyond just people. Teams had to move enormous stones using ramps, sleds, and levers, sometimes over long distances. Imagine hundreds of workers sliding a 20-ton block across sand. lubricating it with water to reduce friction, all while supervisors directed the pace and angle. Communication and trust were crucial. The success of the project depended not only on strength, but also on careful orchestration. Training played a role too. Workers weren't just handed tools and told to start digging. Apprentices learned techniques, from carving stones precisely to handling ropes and levers safely. Knowledge was passed down through generations, creating a culture of craftsmanship that allowed monumental construction to continue over centuries. Perhaps the most remarkable aspect of this workforce was its scale and sustainability. Projects like the Great Pyramid of Giza took decades, yet they maintained quality and precision across millions of blocks. That's not just skill, that's management, logistics, and foresight on a level that rivals modern engineering projects. It shows that the Egyptians understood human resources, scheduling, and workflow long before these concepts were formally studied. The tools were important, yes, but the people made the difference. Without a well-organized workforce, even the best methods and materials would have failed. The Egyptians combined human effort with clever techniques to achieve what still baffles and inspires us today. The Egyptian life. Building the pyramids and massive temples wasn't just a technical feat, it was a reflection of the society that made it possible. To understand how the Egyptians accomplished such monumental work, it helps to look at their daily lives, culture, and lifestyle. The people behind the stones weren't faceless laborers. They were part of a complex society where religion, community, and social structure shaped both work and life. Life in ancient Egypt revolved around the Nile. The river dictated the seasons, the crops, and even the availability of labor. During the inundation, when the fields flooded, many farmers temporarily became workers on state projects. This seasonal labor force provided the manpower for monumental construction without harming the food supply. Villages built near the quarries and construction sites show that workers were organized, fed, and housed. Archaeologists have discovered bakeries, kitchens, dormitories, and even medical stations, suggesting that the state invested in the health and well-being of its workforce. Daily routines were closely tied to social hierarchy. Skilled workers, such as stone carvers, artisans, and supervisors, enjoyed higher status than unskilled laborers. They were trained in specialized techniques from a young age, passing knowledge from generation to generation. Apprentices learned how to use chisels, levers, and measurement tools properly, and how to work as part of a coordinated team. This emphasis on skill development ensured both efficiency and precision on massive projects like the pyramids. Religion also played a central role. Many monuments, temples, and tombs were built to honor gods or commemorate rulers, and laborers were often motivated by a sense of duty to the divine. Workers were part of a larger spiritual vision, believing that their efforts contributed to the eternal legacy of the pharaoh and the favor of the gods. Rituals and daily prayers were common, and many villages had small shrines for workers to pay respects, which created a sense of purpose beyond mere labor. Food and nutrition were surprisingly adequate for such a massive workforce. Archaeologists have found evidence of diets consisting of bread, beer, vegetables, and occasionally meat or fish. Workers were provided with enough calories to perform strenuous tasks, and some inscriptions suggest rewards like extra rations for skilled laborers or those who excelled in their work. This attention to sustenance and care helped sustain productivity and morale, crucial for multi-year projects. Social life extended beyond work. Even in the quarries and construction villages, people engaged in music, games, and storytelling during breaks. Festivals, seasonal celebrations, and communal gatherings strengthened bonds among workers and reinforced loyalty to the state. These cultural aspects were not mere entertainment. They were essential for keeping large labor forces motivated and cohesive over decades-long projects. The lifestyle of ancient Egyptians reflects a balance of discipline, skill, and culture. Their society valued training, organization, and collaboration, which directly translated into the precision and scale of their stonework. Living close to the projects allowed workers to integrate their professional and personal lives, creating a community that supported both monumental construction and social cohesion. Understanding the lives of the Egyptians gives us a new appreciation for their achievements. The pyramids, temples, and obelisks were not just stone and labor. They were products of a society that combined spirituality, practical knowledge, and human resilience. Every block carved and every ramp built was a reflection of the people who lived, worked, and dreamed alongside these incredible monuments. So how did they make every block line up so perfectly? What kind of science were they using without rulers, lasers, or modern gadgets? The science behind precision. The answer is surprisingly clever, showing that the ancient builders had a deep understanding of geometry, measurement, and material behavior, even if they didn't call it science the way we do today. One of the first things researchers noticed is the incredible accuracy of angles. The Great Pyramid, for example, is aligned almost perfectly to the cardinal points. How did they do it? Evidence points to simple but effective tools: plumb bobs, leveling instruments, and sighting rods. By using these, workers could establish true verticals and horizontals. Combined with repeated measurements and corrections, these tools allowed them to create massive structures with astonishing accuracy, all by eye, hand, and careful observation. Surfaces were smoothed and leveled using consistent reference points. Some experiments suggest the Egyptians used water trenches or grooves to detect flatness, a technique similar to modern water leveling methods. By filling a shallow trench with water, they could see whether a surface was perfectly level or sloped. It's low-tech, but it works, and it explains the evenness of temple floors and pyramid bases. Measurement was also key. Blocks had to fit together seamlessly, so they relied on standardized units. The Egyptian cubit, roughly 52.3 centimeters, was subdivided into smaller increments. Carvers used these units for marking stone, ensuring that every piece aligned correctly. Archaeologists have found cubit rods carved from wood and stone, likely used by supervisors to check dimensions on site. Repetition and careful cross-checking meant small errors didn't multiply into structural problems. Angles and alignment weren't the only focus. Researchers studying quarries and construction sites have found tool marks that reveal the Egyptians understood material behavior. For example, they knew how granite fractures, how limestone splits, and how much force a stone could take before breaking. This knowledge allowed them to cut blocks safely and predictably. Even today, engineers marvel at the foresight this implies. People were basically using early structural engineering principles without formal formulas. Experiments replicating these techniques have confirmed their effectiveness. Archaeologists have successfully aligned blocks and structures using plumb bobs, cubit rods, and water trenches, achieving results close to what we see in ancient monuments. While the process was slow, it was reliable. By combining measurement, observation, and experience, the Egyptians could maintain precision across projects spanning decades. What's striking is the balance between intuition and method. While the Egyptians didn't have modern math notation or computers, they clearly had a systematic approach. Every cut, every measurement, every check shows methodical thinking. It's a kind of practical science, not abstract formulas, but real-world problem-solving that produced results still admired today. In short, the Egyptians' precision wasn't magic. It wasn't guesswork. It was careful measurement, repeated verification, and practical understanding of materials and forces. They combined simple tools, standardized units, and observation to achieve results that even modern builders find impressive. They're not just giant stones, they're evidence of humans thinking critically, observing closely, and applying knowledge in ways that stood the test of millennia. The combination of hands-on experience, smart measurement, and careful planning shows a level of sophistication that still shocks engineers today. Even with these breakthroughs, the story isn't finished. Archaeologists and engineers are still uncovering new evidence and testing fresh ideas about how the Egyptians pulled off their incredible feats. Ongoing investigations and new discoveries. Even with centuries of study and decades of experiments, the story of how the Egyptians carved and moved massive stone blocks is far from complete. Archaeologists, engineers, and historians are constantly finding new clues, refining old theories, and running experiments to test what might have worked thousands of years ago. The mystery is no longer about whether it was possible, it clearly was, but about the full range of techniques and strategies the Egyptians used. Recent excavations have shed light on quarry sites like Aswan, Hatnub, and Tura, revealing more evidence of cutting methods and project planning. Unfinished blocks, wedges, and tool marks help researchers piece together the sequence of work, showing that the Egyptians were methodical in every step, from rough extraction to final shaping. Even small details, like the spacing of chisel marks or the depth of grooves, provide insight into the precision and thought that went into these projects. Meanwhile, experimental archaeology continues to push boundaries. Researchers have recreated ancient tools and methods in controlled settings, sometimes successfully cutting large stones using only copper, sand, and water. Other experiments focus on transport, moving heavy blocks with sleds, lubricated ramps, and coordinated teams of workers. Each test adds confidence to existing theories and occasionally challenges long-held assumptions, proving that the Egyptians were constantly innovating. Technology is also playing a growing role. 3D scanning, computer simulations, and digital modeling allow scientists to examine monuments in ways that were impossible just a few decades ago. They can recreate ramps, calculate optimal force distribution, and visualize how thousands of workers might have coordinated their efforts. These tools don't replace hands-on archaeology, but they offer new perspectives and confirm that ancient strategies were both practical and sophisticated. One of the most exciting areas of ongoing research involves subtle variations in tool marks and block shapes across different monuments. These differences suggest that the Egyptians didn't rely on a single method. Instead, they adapted techniques based on stone type, location, and project scale. Granite might require more abrasion and drilling, while limestone could be cut and shaped with simpler chisels. This adaptability highlights a level of engineering flexibility that is rarely recognized in popular accounts. There's also growing interest in the social and organizational aspects of construction. Worker villages, supply networks, and evidence of seasonal labor all hint at an intricate system that combined technical skill with careful planning. Ongoing digs and analyses are revealing how labor was managed, how resources were distributed, and how efficiency was maintained over decades. These discoveries show that building a pyramid wasn't just a technical challenge, it was a massive logistical achievement. The continued research emphasizes that the story of Egyptian stone cutting is still unfolding. Each excavation, experiment, and new piece of evidence adds nuance and depth. moving the field closer to a full understanding of these ancient feats. While many mysteries remain, the exact number of workers, the precise speed of stone shaping, or every small tool variation, the progress made over the last century has transformed our view from wonder and speculation to admiration for practical human ingenuity. Looking beyond Egypt, it's fascinating to see how other ancient civilizations tackled similar challenges using their own tools, techniques, and ingenuity to shape massive stones. Global comparisons and influence. While Egypt's monuments remain the most famous, the story of stone cutting and construction is far from unique. Across the globe, ancient civilizations found their own ways to shape and move massive stones, each adapting techniques to local materials, tools, and environments. Comparing these cultures offers a fascinating glimpse into human ingenuity on a worldwide scale. Take the Inca civilization in the Andes, for example. Machu Picchu and Sacsayhuaman feature massive stones, some weighing over 100 tons, fitted together so tightly that even a knife blade cannot slip between them. Unlike the Egyptians, the Incas rarely used mortar. Scholars believe they relied on a combination of hammering stones with harder rocks and painstaking trial-and-error fitting. The precision is remarkable, especially considering they lacked metal tools for the hardest stones. In Mesopotamia, stonework was more modest in scale, but equally clever. Ziggurats and temples often used mud brick cores with carefully cut stones for foundations and decorative elements. Archaeologists have found evidence of copper and bronze chisels, wooden levers, and rudimentary cranes or pulleys. While not as monumental as Egypt's pyramids, Mesopotamian builders demonstrated careful planning, standardization, and an understanding of weight distribution, essential principles for construction. Further north, in Europe, the megalithic structures of Stonehenge and other Neolithic sites reveal another approach. Stones were quarried, shaped minimally, and transported over long distances using sledges, rollers, and possibly lubricated tracks. The sheer effort involved shows a combination of ingenuity, social organization, and sheer human determination, echoing what we see in Egypt, even if the techniques differed. Across the Pacific, Polynesian cultures also engineered massive stone structures. In places like Easter Island, the Moai statues were carved from volcanic tuff and transported across the island using ropes, sleds, and clever leverage. Experiments suggest that teams could walk the statues upright by rocking them side to side, showing that creativity often solved practical problems when technology was limited. What's striking across all these civilizations is that the challenges were similar. Heavy stones, difficult terrain, and the desire for impressive monuments. The solutions, however, were adapted to local resources, cultural priorities, and available tools. While Egyptians used copper, sand, and ramps, others developed methods tailored to their environment. The common thread is ingenuity. Humans everywhere found ways to overcome enormous physical challenges with the knowledge and materials at hand. Studying these comparisons helps us appreciate both the uniqueness and universality of ancient engineering. The Egyptians were pioneers in precision and scale, but they were part of a broader story, a global tradition of solving monumental problems creatively. The innovations in one civilization may not have been directly shared with another, but the results speak to a shared human drive to build, to create, and to leave something that lasts for generations. These global parallels also give modern researchers perspective. By understanding how different cultures approached similar challenges, archaeologists can better interpret the tools, techniques, and organization used in Egypt. Implications for history and engineering. The breakthroughs in understanding Egyptian stone cutting are more than just archaeological trivia. They reshape how we think about history, human ingenuity, and engineering itself. For centuries, the pyramids, temples, and obelisks seemed almost supernatural in their precision. Now we know that the feats were achievable with simple tools, clever techniques, and well-organized labor. This insight changes the story from one of mystery and speculation to one of admiration for human problem-solving. First, there's the historical impact. Knowing how the Egyptians worked gives historians a clearer picture of daily life, social organization, and state capacity in ancient Egypt. The construction of monumental structures wasn't random. It required planning, skilled labor, logistics, and management. Workers weren't slaves in the Hollywood sense. Evidence from worker villages shows they were fed, housed, and cared for, with specialized roles and training. This highlights a society that valued skill, planning, and coordination. From an engineering perspective, the implications are equally profound. Ancient builders mastered physics and material behavior intuitively. They understood leverage, friction, and stress distribution without formal equations. They knew how limestone would split, how granite could be abraded, and how to move massive blocks over sand or ramps without catastrophic failure. Modern engineers studying these techniques gain valuable lessons in resourcefulness and problem-solving. It's a reminder that sophisticated engineering doesn't always require advanced technology. It requires understanding materials, planning, and execution. These discoveries also challenge long-held myths about what ancient civilizations could accomplish. For decades, sensational claims about aliens or lost super technology captured the imagination, overshadowing the real brilliance of human skill. By reconstructing methods through experiments and analyzing tool marks, researchers have shown that humans alone were capable of these feats. That alone is inspiring. The scale of ingenuity and collaboration in ancient Egypt is staggering and should be celebrated for its own merit. Another implication is how we approach preservation and education. Understanding the methods used allows modern conservators to care for ancient monuments more effectively. They can anticipate how stones might shift or erode, how stress points form, and how ancient techniques affect long-term stability. Educators can also use this knowledge to teach engineering, history, and physics in engaging ways, connecting students with real-world applications of problem-solving. Finally, this research underscores a timeless lesson. Ingenuity is universal. The Egyptians didn't have lasers, cranes, or electricity, yet they built structures that have lasted thousands of years. They combined creativity, observation, and collaboration to overcome immense physical challenges. For modern engineers, builders, and thinkers, it's a reminder that resourcefulness, careful planning, and teamwork can achieve extraordinary results, sometimes rivaling what modern technology can do. For more incredible stories like this, hit that subscribe button so you won't miss out. Thanks for watching.